can really build a 30 DOF humanoid robot for just a little over 6,000 US dollars. Meet ToddlerBot from Stanford University, standing 56 centimeters tall and weighing 3.4 kilograms. This little robot is almost entirely 3D printed. From 3D models and joint actuators to control code, everything is open source on GitHub. Don't be fooled by its size. It can do push-ups and pull-ups, perform coordinated two-arm tasks, and even push a cart. Pretty cool, right? So how does it actually work? ToddlerBot runs on off-the-shelf dynamic servos. They are compact, affordable, and come with angle feedback, making them accessible to hobbyists and labs alike. But there is a catch. Take the XC330, for instance. Its output shaft is only supported by a Teflon bushing, which means it develops a lot of free play and wears out quickly if subjected to weight and transverse loads. Stanford's team tackled this weakness by combining three different transmission structures: spur gears with metal bearings mainly used in the arms. The motor drives a secondary shaft supported by bearings through extra spur gears. The motor delivers torque, while the bearings handle side loads, reducing stress on the motor. Bevel gears are mainly used in the waist, where space is tight, but two orthogonal actuation DOFs are required. Two pairs of bevel gears let two motors work together, solving layout constraints while boosting strength. Linkages used in the knees and neck. Motors drive the joints through linkages, giving a more compact structure, low inertial, and better load distribution. For example, the neck motor hides inside the head, and the knee motor is moved up into the thigh, reducing leg inertial. These three solutions effectively compensate for the limitations of small servos. In total, ToddlerBot uses 5 types of dynamic motors deployed strategically: XM430 for high torque joints, XC330 for smaller joints, and dual DOF integrated servos for arms and hips, saving space while keeping DOFs intact. In other words, instead of just stacking expensive parts, it relies on smart transmission design to make low-cost servos capable of complex movements. Add to that an almost fully 3D printed frame, plus detailed assembly manuals, and it's highly reproducible. But good hardware alone isn't enough. Robots still face a huge challenge: the scene-to-real gap. ToddlerBot's solution is to build a high-fidelity digital twin. Step 1. A 3D printed calibration device locks the robot in a specific pose. In under a minute, it zeroes the joint so all starting angles align. Step 2. System identification is used to measure motor friction, damping, and other parameters, which are then fed into simulation for accurate motor models. These 2 steps are the key to achieving zero-shot scene-to-real. Beyond that, the team used Mujoko for physics simulation, along with keyframe debugging and trajectory validation tools. This way, they can first generate smooth coordinate actions in simulation, like push-ups and pull-ups, verify them, and then transfer them directly to the real robot. With a sufficiently precise digital twin, the gap between simulation and reality can actually be bridged. ToddlerBot's legs are trained with reinforcement learning. It learns walking and turning strategies in simulation, then transfers them to hardware. The arms rely on imitation learning. A human teleoperates the robot, which collects demonstration data. During full-body coordination training, the waist and legs are stabilized with layered PD control. In just 20 minutes, they collected 60 high-quality full-body motion trajectories. These were used to train diffusion policy, a generative imitation learning method that produces diverse natural motions instead of rigid scripted paths. How are the results? ToddlerBot achieved a 90% success rate in two-hand collaborative tasks like carrying toys, and around 75% in full-body manipulation tasks. Even more impressive, the team combined skills: imitation learning for grasping the cart handle, reinforcement learning for walking while pushing. Just like a child, first learning to grasp, then to walk, and finally to walk while pushing. This dual chaining approach shows a path toward more general and intelligent humanoid robots. ToddlerBot isn't just about showing off a few tricks. It represents a roadmap for the future of humanoid robotics. Clever mechatronics, precise digital twins, advanced control methods, and steel chaining, all working together to bridge the seam to real divide. Don't forget to like and subscribe so you won't miss more amazing robotics.